All right. Good evening, everyone. Welcome to Crossroads of Ideas, the upside of AI failure. My name is David Fields, and I'm the Associate Director of the Center for East Asian Studies here on campus. I'm a historian. I also teach in the history department and in the international studies major. So today's event marks the second installment of our three-part mini-series on productive failure in science. Crossroads is a program series presented by Illuminating Discovery Hub at the Wisconsin Institutes of Discovery and developed collaboratively with UW-Madison and Discovery Building partners. Crossroads of Ideas brings together campus experts and community members to explore thought-provoking topics at the intersection of science, society, and the arts. Since its launch in 2014, this series has been a cornerstone of public programming at the Discovery Building, fostering dialogue, curiosity, and connections across multiple disciplines. We're delighted to have you with us tonight and to join this conversation. So tonight we're going to explore a topic that is fundamental to how innovation actually happens, and that is productive failure. Okay, failure is often framed as something to avoid, especially in a field moving as quickly and as publicly as artificial intelligence. But as we'll explore tonight, when AI falls short, it can reveal just as much as when it succeeds. And to help us, we have Dr. Rob Nowak, who will join us in a minute, from the Computer, Data, and Information Sciences, whose research focuses on how we understand, train, and evaluate AI systems. First, I'll explain a bit about my own involvement in AI object detection in a project that I ran with some students that did not quite go as planned. And then Rob will help us zoom out, examining how failure functions within AI development itself and what these moments of breakdown can teach us about innovation, responsibility, and resilience. And then I'm sure we'll have some time at the end of this conversation for Q&A from the audience. Okay, so I will get started with my own background about how this project came about. So I am a historian of U.S.-Korean relations. I'm a specialist in this. And in 2011, as a graduate student, I had the amazing opportunity to travel to North Korea. So at that time, it was neither illegal nor especially dangerous. At least it didn't feel dangerous at the time. It was an amazing opportunity for someone studying what I study. So I got to spend about 10 days in North Korea. We actually got to travel all around. So here's a picture of me with my two North Korean binders. We're at the DMZ, actually at Panmunjom, actually looking into South Korea. So you'll see hundreds of pictures of people standing on the south looking into North Korea. There's not too many pictures taken from this vantage point. So it was an absolutely life-changing experience for me to go there. And one of the things that struck me as we were going around the country was, one, the dilapidated infrastructure, but just a complete lack of automobiles. So we drove we drove 728 of North Korea's 750 kilometers of paved roads. Okay, so we saw almost the entire road network, and we saw almost no cars the entire time. And many of the cars we did see looked like this. Okay, so they were trucks with gasifiers so they could burn wood. So they're actually wood-powered trucks on the road. And this stuck with me for many years. It got me really interested in North Korea, but actually questions of North Korean infrastructure as well. So while I'm primarily a historian of US-Korean relations, I've had this side interest in North Korea, and I really wanted to do something empirical related to North Korea, especially with satellite data. So there's not a lot of hard data on North Korea. Not a lot of stuff comes out of North Korea, but I knew that there was a large body of satellite data. I had been across the country, and I was trying to think of a way that I could use this. I know, Google Earth has, more than you could possibly imagine, but I never could find a way to do it until I had coffee about 4 years ago with a man named Dave Schrader, who's now the director of National Security Research here at the University of Wisconsin. And I told him, my idea that I wanted to do something empirical about North Korea, and he said, oh, there's a whole program that does just that. It's called the Terline Project of the National Geospatial-Intelligence Agency. And of course, I'd never heard of it. But right away, I knew, OK, this is a great opportunity. And what Terline does is any faculty member can put together a team of students and go to Terline and say, hey, we've got a team. We would like a question. and then Terraline will pitch you a question, and then they will give you all the satellite imagery they think you need to be able to answer that question. So I thought, this is a perfect opportunity. So I got a team of students together. Actually, it was just me and one other student at this point. And I told Terraline, I have a team. I would like to do something related to North Korea. And actually, I would really like to do gas stations. Because I thought, if there's one way we would know there would be cars increasing in North Korea is if we see more gas stations being built. So I said, let's do gas stations. And they looked at me like I was crazy. And for good reason, because they're like, you would have to search all of North Korea, like every square kilometer to find gas stations. That won't work. And I thought, yeah, they're right. So they said, how about you survey automobiles? How about you try to come up with a methodology to try to figure out how many automobiles there are in Pyongyang? And I thought, okay, that sounds kind of in the lines of what I was thinking anyway. But then I countered and I said, why don't we do Hamhung, North Korea's second city? Because even though it's the second city, it's an order of magnitude smaller. So they said, okay. So they pitched us, we will give you all the satellite data that we have on Hamhung. You come up with a way to survey automobiles and try to come up, basically what they wanted is the number of automobiles in Hamhung going up or is it going down? That simple. So I'll say from the beginning that we would not have done this project if we did not think that object detection models could do it for us. All right, I am not a technical person, and I should say that when I say we, I mean the students. Because I'm a historian, I'm an area studies specialist. I'm not a technical person, so I was completely dependent on students to do this. But I knew that such things as object detection models existed. And so I thought, shoot, I'm in a university of 55,000 students. I'll find someone who knows how to do this. So I went to the one STEM student in my class and said, hey, do you know anything about object detection models? He said, no, but I think my roommate does. And within about 2 weeks, we had a group of students doing things like this, okay? So we got satellite data from NGA, shots of Hamhung. We actually used a lot of data from Google Earth too, which was actually better and easier to work with than what NGA gave us. And so we started using object detection models, specifically one called YOLO, You Only Look Once, which is a pre-trained object detection model that is really good with automobiles. And as we started doing this, we realized right away we had a problem. Okay, we had a tremendous amount of false negatives. It actually functioned pretty well most of the time. If you look at this image here, you'll see these red, the red text, the red boxes with white text is where it detects an image. So if we zoom in a little bit, you can see it's getting a lot, but you can see it's also missing a lot. So these are automobiles right here. These are automobiles. There's an automobile there. So it's getting a lot of them, but it's missing a lot as well. And as we tried to figure out what was going on, we quickly came to realize that the problem was, at least one of the many problems, was the resolution of our images. Okay, so YOLO is trained typically on data that looks like this. Okay, so it's very, very high resolution data. When they use overhead imagery for YOLO, generally it's drone imagery, which is about at a resolution of 30 centimeters or higher, meaning that one pixel on the screen would represent, let's say, 30 square centimeters of real life. All right. The best data that we could get from the NGA was 50 centimeters. That was the absolute best case scenario. All right, and we were also dealing with satellite imagery, which meant it's often off nadir. So it's not looking straight down, it's looking over at an angle, meaning there's a lot of shadows, okay? We also had problems with foliage. It turns out that Hamhung has a lot of tree-lined streets. So there was all sorts of reasons that our data was not working well. We also realized that we did not have the abundance of data that we expected that we would have. It turns out, actually, NGA will only provide you commercially available imagery. They will not, I'm sure they have lots of top secret imagery of North Korea. They will not give that to you. Commercial satellite data only. And it turns out that there's not a lot of commercial satellite data of North Korea because not a lot of people are buying commercial satellite data of North Korea. So the coverage of the city of Hamhung was not as good as we thought. Also, when satellites take an image, they take a long rectangle and they don't care whether they've cut the city in half or not. It's whatever rectangle was convenient for them. So we had to throw out a lot of images just because they didn't have the coverage that we needed. So our models weren't working. We didn't have as much data as we thought, so we were faced with a choice. Either we could give up on this project and ask NGA for something else, or we could brute force it, okay? So we decided that we would brute force it. And this is where my background as a historian really came in handy. I spent 7 years as a historical document editor at the Center for the Study of the American Constitution, transcribing 18th century documents and reading them out loud to another human being, an activity that's been going on our campus since 1932, actually. And when we would read these documents, here's how you read this document. Cap P Providence, Cap SEPTR point, Arabic 8, superscript TH point, Arabic 1788 point, next line, Cap HOND point, Cap SIR, comma, Cap by permission of divine Cap Providence. I could go on. So I spent 7 years of my life doing this kind of thing. And so I knew that humans can do really, really tedious work. And if you get the right undergraduates, you can do anything. So we expanded the team massively to 9. And what we thought was going to be maybe like a 2 or 3 month project turned into the better part of a 2-year project while we manually counted cars in the city of Hamhung with the images that we had available. Like I said, it ended up taking a very, very long time. It was very tedious, but actually it was a great experience. For a couple of reasons. One, we were actually able to count the vehicles and do a statistical analysis on imagery over 10 years and argue fairly definitively, statistically, that the number of automobiles in Hamhung is going up. There's almost no question about it. We also were able, for the first time ever, to create a baseline estimate for the number of small passenger vehicles in North Korea that's based on survey data. Okay, and by the way, it's about 34,000. All right, by comparison, there's probably between 2 and 3 million vehicles in the state of Wisconsin. Okay, and there are 34,000 passenger vehicles in North Korea. But because we did it this way, we actually got to learn the city of Hamhung really, really well. All right, really well. And we were able to gain all sorts of other evidence to make our point even stronger. For example, we were able to show over 10 years, Hamhung went from having 0 stoplights to having 4 stoplights. Okay, that's a strong indication that there are more vehicles on the road if you're adding stoplights, okay? We also were able to show that they added 4 gas stations, going from 2 gas stations to 6 gas stations in the city. However, they did not add a single parking lot. This was something else we realized. So this is the only lined parking lot in the city of Hamhung, and not another one has been built. So now we're already laying the foundation for someone in the future to go back and look at Hamhung someday and say, are they building more parking lots? Okay, that would be the sign that the numbers are really, really increasing. So this was published on Terline's website. If you're interested, you can go read about it. You can see my name and the name of all the students there. But finally, the interesting thing about it is it set us up for the work that we're working on right now. Because while we were spending 10 years surveying Hamhung, we found what we referred to as the world's saddest water park. And it was the world's saddest water park because it never had any water in it. And when we realized this, we thought, surely there are other water parks in North Korea, and they also probably don't have water in them. So now we've spent the last 14 months searching all of North Korea for water parks. We've found 14 and doing analysis using NDWI of whether they have water in them. And hopefully that work will be published in the next 2 to 3 months by the NGA's Terline project. So that's a little bit about the research I did. So now I would like to invite Rob Nowak up to the stage, who is the Grace Walla Professor of Data Science and the Keith Jane Nunsuch Professor in Engineering at the University of Wisconsin-Madison, as well as an adjunct professor at the Toyota Technological Institute in Chicago. His research and teaching focus on artificial intelligence and signal processing. His current work explores the mathematical foundations of deep learning, develops algorithms for data-efficient machine learning, and examines the intersection of AI and human cognition. Please join me in welcoming Rob.
Thanks, David. Can everybody hear me? Yeah, good. Okay, well, that was super interesting to hear about David's work. And I'm very curious about North and South Korea. I have some close South Korean friends, and it's a totally different world over there. So yeah, I don't know. I'll have to see if I can get over the border sometime. Okay, so what was this called? Something about the benefits of failures or something? What could that mean? So this picture is kind of trying to illustrate how AI systems are engineered. I think a lot of people understand this right now. Nobody's sitting down and coding up an AI system. We're giving it a lot of examples of data, and then we're training it on that data. It's basically learning from the data automatically, and then we produce a system that takes in inputs and produces desired outputs. Now, in the lab, we have this well-curated data set. It has the information we think is going to be relevant for whatever task we want this AI system to do. Once we've built it in the lab, we deploy it into the real world. That's what I'm calling the wild here. And what I'm trying to illustrate is the wild is wild. It's a lot different than the lab, and there are a lot of unexpected things that will come up, and we want our systems to be robust, resilient, and trustworthy in those environments. So this is kind of just an illustration of maybe 3 of the different types of failure modes, and I think some of you will be familiar with some of these. Like the first one here is data bias. There were a lot of kind of high-profile newspaper articles about this problem where people built AI systems for facial recognition. The data sets that they trained on pretty much looked like this audience, mostly white, a few people with darker colored skin. And that meant that the systems had very high accuracy for light-skinned people and not so great accuracy for people with darker skin. And that led to a lot of uproar and problems, and people didn't like it, and we figured out how to fix that. I mean, a simple fix would be get a better data set, make it more balanced. There are other ways to do it. We just might not have all kinds of representation of every type of person, so you can build in safeguards so that you get accuracy across all subgroups of people. Another problem is distribution shift. This is basically the idea that I have some data in the lab that I train on, my system works great there, I get really high accuracy, and then something changes. The real world isn't, it's sort of like the training data, but a little different. And that even a little different, a little bit of a shift in how the data looks can really cause some strange failure modes of the systems. There may even be some strange outliers, like, for example, self-driving car encounters some construction zone that looks nothing like anything it was trained on. It might just kind of totally break down. Or maybe there's some weird weather system that was never in the training. That could also cause a problem. And then another issue is overconfidence. It's a little hard to go into the details, but these systems, these AI models, they have their own internal confidence about the predictions that they're spitting out. Unfortunately, that confidence isn't always calibrated with real-world truth. And so what can happen is you can get systems that produce very confident, wrong predictions. And that could be catastrophic in, say, medical diagnosis. If I have an AI system trying to diagnose somebody's ailments, if the patient's profile is sort of different from everything that was trained on, it might have high confidence in a wrong diagnosis. That would be bad. So here, I'm just sort of showing the top is what we just talked about, the problems, failure modes. Then below this is all the stuff that's very hard to get our hands on, very hard to get our minds wrapped around. First of all, these are what we call black box systems. The unfortunate truth of the matter is that nobody really understands how ChatGPT does what it does. Not the guys who are building it. Sam Altman doesn't know. Nobody knows. They try to learn. We're probing these systems, trying to get a better idea about their internal workings and how they perform what they do, but they are black boxes. They're highly uninterpretable. That's a problem if we're trying to say, why did it do this weird thing in this case? We don't know. This proxy problem, this is just saying that, look, we take a model. These are deep neural network models. I don't know if that means anything to some of you, but it's basically a model that they train for a desired input and output in a system. We can get very high accuracy on the data in the lab, and we think, okay, now we've got a great system. But that lab data, again, might not really align with everything it's going to encounter in the real world when we deploy it, and it could actually do very bad unintended behaviors, crash a car, for example. And then these systems are, once they're out there, they're kind of continually going, and they're interacting with data and the real world, and then we're collecting more data based on those actions. And that can kind of cause a feedback loop that might actually drive the system into an even worse configuration. So we have to be mindful of that too. Things are changing after we deploy it. Our world today is different than it was a couple of years ago when we didn't have ChatGPT. It's affected all of us in ways we don't really understand yet. Okay, So what can we do? We can start to say we need to build in trustworthiness, reliability, robustness into these systems. And here are just a few high-level ways we might do this. One, we could say maybe we just want these systems to not always be confident and somehow know when whatever's coming in to the system is something very different than what they've been trained to recognize or understand. So we give it an option. Output what you think is the right thing, but if this looks really different from what you were trained on, just say, I don't know. That in and of itself is very valuable. Now we have systems that at least can react appropriately when they're in a situation that they really don't understand. Also, transparency and interpretability. So there are ways to sort of look at these very, very large neural network models and start saying, well, what could we do with these models? How could we architecture them a little bit differently so we can get signals out, we can probe the insides to figure out, oh, something went wrong, we got the wrong output in this case, where did it go wrong? We can start engineering some of those little places to peek into the model, right into the system. And then, of course, once we deploy these systems, we can't just deploy and then let it run wild. We have to continually monitor it, maybe retrain it, fine-tune it, as we say, so that it is continually improving and keeping up with an ever-changing world. All right, so now I'm just going to talk about one or two of these issues, and they're a little bit related to what David talked about. And these are problems I've actually worked on with some of my students. And I'm just going to give you a little toy version of it. So imagine we're building a robot, and that robot's going to walk around, and we want it to recognize vehicles. And just to keep things simple, let's suppose in the lab we've trained it to recognize when it takes an image in whether the vehicle is a car or a bus. Okay? Now, we get super high accuracy on cars and buses. We've trained them on a really nice, clean, labeled data set. I have an image of a vehicle. I say that one's a bus. I have another image. I say that one's a car. That one's a bus. That's what the robot is being trained on. Then we let it walk around outside, and all of a sudden it sees this new vehicle. It's a bike. We all see that, but it doesn't know what a bike is. We forgot to train it to recognize bikes too. So what a typical or sort of a system could do is it might just say, well, that bike best guess is it's a car, and it might say car. Of course, we don't want it to do that. We want it to say, I don't know what this is. So how would we do that? So these are basically three approaches. We call this out-of-distribution detection. The distribution is the distribution of the data that we've trained on. Out of distribution means something different than what we trained the machine to do. So the first one is what people sort of started off doing. They said, well, these models do have some internal mechanisms that indicate how confident it is about its output. Maybe we can just use that. But as we already talked about, these can be confidently wrong many times. And so that generally doesn't work very well. Second approach, which is probably the one we'd all take, we'd say, well, we were dumb. We should have included bicycles. And if we would have only included bicycles, it would have recognized it as a bike and wouldn't have said car. But of course, bikes aren't the only thing it might find out there. Maybe there are drones. Maybe there are scooters. Who knows what else it's going to run into? So we can't anticipate everything that these systems will encounter once they're in the real world. So that brings us to this third approach. And this is what we actually did. We said, let's think about it this way. We can put the system out in the real world. It'll start taking in data from the real world. Say taking pictures of the real world as it walks around. Now, those are not labeled. Nobody's telling it. Nobody's with it saying that's a bike, that's a car, that's a scooter. It's just taking in these unlabeled images. So we have a bunch of those, maybe essentially unlimited. It can just take in a lot of data. But then we also have our training data, the original data we trained on. And so what we're going to do is we're going to say, let's take in all those unlabeled images. Let's try to say as many of those as possible are different than what I was trained on. Okay? But at the same time, let's make sure that the system still does high accuracy on the things, the known label data that we originally started with. So we're sort of setting it up as two objectives now. Try to say everything's different, but at the same time, you still have to say the stuff we know is a bike, and we know is a car, and we know is a bus. You still have to label that correctly. So let me try to illustrate this with a picture. Now, what I want you to imagine is that the pictures come into the robot. The robot extracts, let's say, two features. I won't go into what those features might be, but just imagine two descriptors that kind of characterize what that vehicle's shape or outline or whatever is. Now with those two features, we can take each example in our training set and plot it as a point in 2 dimensions. One dimension is one feature, the other dimension is the other feature. So each vehicle in our training set is a dot in this 2-dimensional feature space. And we know some of them are buses and some of them are cars. And if we have good features, we'll see clusters like this. Oh, the buses are sort of in this part of those 2-dimensional feature space, and the cars are over here. Now we send it out into the wild. It just gets a bunch of unlabeled images. And those unlabeled images will extract the features, but we don't know if they're buses or cars or something else. So we color them gray. So we look at this and we say, well, you know, we're probably that one's probably a car there, and that one's probably a bus there, but what about all the others? So in fact, these might be truly out of distribution. Maybe those are bikes and scooters. We don't know that, though, and the robot doesn't know it. So what we're doing is we're basically saying, make sure you classify correctly the orange and blue dots, the cars and buses that we know about in our training set. Get those right, but then try to say as much as possible is not like what we were trained on. So it kind of sets up this green boundary. So it would say, this is the stuff I think I know what they are, and those things it's not confident about. Those are where it's going to say, I don't know. Okay? So this turns out to really be the best of those 3 options that we just talked about. Now this one is very related. We call this distribution shift. So what this means is that we still have, in this case, we're looking at cars. We're interested in vehicles, just like David was. And there are cars in both cases. We're not trying to discover new things that it wasn't trained on. It's just that the data looks a little differently. Maybe we started off with higher resolution imagery, but then when we field it, we have lower resolution. I've really exaggerated the problem here, but you get the idea. So it could be that we trained at high resolution, but then when we actually want to deploy it, we have to work with lower resolution. This is what David had. Another thing is, we could train our self-driving car on all kinds of images and videos from the road, but if we only trained on nice weather conditions, will it recognize this car once we're in a snowstorm, right? So these are things where we'd like the system to not fail. We don't want it to say, oh, when it's snowy, I don't know what that is. We want it to say, that's a car, it's a car, but it looks very different than what it was trained on. So how do we handle that? And this is going to be a very high-level picture here. But again, imagine we had just 2 features that we extract from these images. And initially in the lab, we trained only on vehicle images in nice conditions. And so the original lab train model would say, oh, vehicle, but both of these it would say, I don't know, not vehicle. I don't know what those are. Well, one's a deer, it's not a vehicle. The other is a vehicle, but in snow. So what we can do now is we can take all that data, again, that we might collect once the system's out in the real world, and do what we call fine-tuning to kind of adjust this model so that it correctly says, oh yeah, that is a vehicle, but that still is not. That is something I don't know what it is. Okay, so this is how we're basically combining data from the lab with all the data that we start to gather once the system's in the real world. That can help us overcome this problem of out-of-distribution detection, this I don't know problem, but it can also allow us to adapt to new conditions, different resolutions, different weather conditions, and so forth. So this is my last slide. I'll wrap up now. So we want these systems to be optimized for a kind of stability or robustness, not just accuracy. It's not just about getting the highest accuracy on the data that you have in the lab. It's about making sure these systems are going to work once you get them out in the real world. If they will degrade, and they must, right? I mean, you can't possibly be robust and resilient to everything, but we don't want them to catastrophically fail. We'd like them to gracefully degrade as we come into situations that are more and more different from what we trained on. We need these things to be aligned, as we say. That means that they have to be trustworthy and they have to be interpretable. We want to be able to go back and say, why did it do this crazy thing in this situation? That has to be part of the engineering of these systems. And then they're going to have to learn and adapt continuously. So it's not a train once and deploy and just leave it go forever. It's a continual cycle. Train, release into the real world, refine, fine-tune, as we were talking about. And so that's all I have. And we'll carry on the discussion now, I guess, right? Okay. I'll just put these here.
All right. So I meant to say when I was up there, when we first had this problem, and thought it was a resolution problem, the first thing that we'd have tried, which seemed to be the obvious solution, was take the training data and try to degrade it, since it was already labeled, retrain YOLO on now the much lower resolution data, and then turn it loose on our resolution data and hope that that would work better. And what we found is it did make it a little bit better, but not a lot better.
Yeah.
And so I guess, knowing that we tried that, if you were in our shoes and we're doing this project, how would you approach it? Or, if you're getting these bad results, how would you try to fix that?
Yeah. So I cannot take credit for this. I asked one of my students, and it turns out that she actually worked on a very similar problem. They were not trying to count the number of vehicles from aerial views, but they were trying to count the number of people, crowd size calculations. And they ran into the very same problems you did. Even if you adjust for this resolution business, you've got the shadows, you've got the foliage, all these other things that are occluding or confounding the detection of people or vehicles. And what they ended up doing was kind of an interesting approach. And she tells me this is basically the state of the art now. Instead of trying to count vehicles, let's say count vehicles. They were doing people, but let's say vehicles. Instead of trying to count them, basically saying there's a vehicle, 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 you want to kind of create like a intensity map of vehicles. So you turn it into this sort of continuous density or intensity estimation problem. Just the way like we could count every single raindrop. That's not what we look at. We look at sort of the sort of density of rainfall, right? And so she said that's what they ended up doing. So you get a density map, not individual counting, and then from that you can say, well, how many vehicles were in this area? Well, you just sort of add up all that density. That gives you a number. And that turned out to be a much better, much more robust way to get an estimate. Of course, you'll have to round. You might get a number like 36.3, but then you'd say, okay, that's kind of like 36 cars, right? So that turned out to be their solution, and she tells me that's pretty much the state of the art for this kind of problem now.
Okay.
And it's still evolving, but it's a hard problem. But I think what you said was a great thing. You said, we can do it, the students and I could do it, why can't the AI system do it? And I think they can, but maybe they'll do it differently than what we're doing.
One of the problems that we realized right away, black cars on black pavement is a real problem. They're almost ghost-like. And you can see them, but to try to tease that out, it just didn't seem it was there. But this idea of this intensity it would work great for the question that we wanted, which was not strictly speaking, what is the exact number of vehicles? It was, is the number of vehicles going up or going down over time?
I was just wondering, like I guess you and your team went through gazillions of images and did this, but if I were going to do a survey to say who are our people going to vote in the next election, of course we don't ask everybody. We ask a representative subsample, and then we estimate then from there.
Right.
Could you do that in your problem?
See, this is how we became aware of the parking lot problem.
Because there's only one.
Because we thought, okay, let's instead of doing the whole city, let's look where the cars are. So let's find parking lots, and then let's just count cars in parking lots. And do parking lots get fuller? Do they get less full? And then we realized there's one parking lot in the whole city, and it has space for 25 cars, and it's empty all the time. And so then we thought, well, where is the city center? Where could we expect cars to congregate? And then we learned nowhere. There is a city center, but it's actually where the train comes in. And in the city of Hong Kong, people mostly walk. And so you see a lot of people there, but you don't see many vehicles. We actually had the amazing good fortune to actually be able to speak to someone who had just recently left Hong Kong within the last 3 years, and we were able to interview them.
Like escaped.
Like a North Korean defector. And we were able to interview them, and we were trained very carefully on how we ask these questions, not to lead them, and ask them what people use automobiles for. And they said, it's mainly people who have money, senior officials, people who have made money in the black market, and they're just using them to run across town. None of these vehicles are owned by individuals. And so the pattern of usage was so different than what you would expected. Like, because one of the questions we asked was, do people commute to work? Is there a rush hour in the evenings? No, there's not. So I mean, there were places probably somewhere in the city where vehicles would be more common and we could focus out there, but we could not make any sense of where those places would be, especially with the paucity of images we have. So when I say like we didn't have many images, I mean we had less than 20 images over 10 years that would be able to meet all of our criteria, covering the entire city, being 100% cloud free. I guess another question, and this is really important to me because, like I said, I was dependent on students for everything that I did here.
Yeah.
Because I am not a technical person.
Yeah.
I'm a historian. So I guess what would you say are the easy entry points for using AI to do research for someone like me?
Yeah. Well, I mean, I think I can't speak for all of them, but I'm pretty sure every undergraduate knows how to use ChatGPT or something like that for research or help with their schoolwork. So we're all using it, at least, or most of us in that form. Everybody's probably Googling, and then you're getting Google AI. So we're using it, but to do something more like what you wanted to do, I mean, that's getting closer. Like if you want to, these slides, I knew what I wanted to say, and I used something called Notebook LM to make them cool. Yeah. Some of them, I hope they were kind of cool. They look kind of cool to me. They're better than I could have made. And so, and that's just kind of like pretty straightforward to use. So now if I wanted to take one of your satellite images and count the cars, I wanted to do this. I didn't do it, but I wanted to just throw that into one of these systems and say, show me where all the cars are and see how well they could do. I also talked to some of my other students about this, and they said that they thought it would do pretty well, but maybe not as well as the other students' density map approach, but they're getting better and better. This idea of counting how many people or things are in a scene is something you can imagine would be useful to many people commercially. Like, hey, how many people showed up to the Badger basketball game, right? They might want to just keep track of that, right? So now you can just do it with some drone footage and throw it in there, and hopefully it'll give you a pretty good estimate. So I think it's going to get a lot easier. You know, I'm teaching an advanced undergraduate course on some aspects of AI and machine learning, as we call it. And in the past, a component of this course was to code up in software some of the ideas, some of the machine learning algorithms and techniques. Now I don't call that programming or coding. I'm calling these things computational experiments, because really all they have to do is they can actually take like the homework problem, throw it into Gemini, ask Gemini to write a computer program that implements this algorithm, and then they can put it into something called Google Colab and just run it right on their computer. All this is running in the in the cloud. They don't have to install anything. They don't really have to know anything, although if that program doesn't do exactly what you want, if the outputs aren't working as well, then you're kind of stuck again. You have to go in and say, well, what exactly was this Python script doing for me, and where was the mistake happening? And that gets back to this whole interpretability thing. So I think that's the bigger problem. People will be able to use AI pretty easily. It's just whether you'll know if it does. It's great if it works. Like, I don't know how it made the slide, right? I said, this is what I want in the slide. It made the slide for me. I don't know exactly how it did it. There's absolutely no way I can go back, oh, that's perfect, just change this little thing. We're not really there yet. The AI systems can't edit things that easily. So yeah, as I said before, nobody really knows the insides of these giant AI systems like ChatGPT and Gemini and things like that.
Yeah, we in our search for the water parks, this is something we brute forced again, but it's actually not as hard because you know that it's going to be cities of a certain size that have water parks, and we can search North Korean media and find references to water parks. But when Gemini got added to Google Earth, we thought, oh, well, let's just ask Gemini where the North Korean water parks are. And so we tried it, and it was very, very disappointing in that we keep all of our data actually in Google Earth.
Yeah.
So we've been labeling North Korean water parks in Google Earth, and we asked Gemini, and it found the one that everybody knows about.
I see.
The one that actually foreigners visit, probably because I'm guessing is pulling large language models into it, and this is the one that's referenced all the time. It couldn't find any of the other 12 that we had already identified.
Yeah, and
I don't know
you
why.
had identified them, but it's not published yet.
No, it's not published, but we keep a shared Google Earth project.
Yeah.
So, and I don't know how often it's training itself on other
new
people's
stuff,
data,
yeah.
but we have a data set in Google Earth that it's not published yet, but it's shared with our team,
Yeah.
identifying all of them.
Yeah.
And it's been there for probably about 8 months.
Yeah.
And I don't
So
know.
far.
So
It hasn't
far,
been ingested somehow into the
yes.
model. Yeah.
Yeah.
Interesting. Yeah, I can't tell if North Korea, it sounds weird. It also sounds like a eco paradise with no cars. I don't know what to make of it.
If there was more food, maybe it would be
that
it would be
doesn't
an
sound so much like
eco paradise.
Yeah.
Maybe I'll ask one more question. And you kind of raised it here, but I wonder when the average person will be able to understand how AI makes decisions, or will we never be able to understand that? Because that was one of the frustrating things to us is what parameter could we change? Because when there's two cars right next to each other that look identical, and it says this one's a car and this one is not, what is the decision process leading to that?
Yeah. Well, so first of all, let me say in a familiar form of AI, like these chat systems, right? There are mechanisms inside by which it's sort of performing its reasoning. That's called chain of thought. We use a lot of words that we use for our thinking and then apply them to these systems for better or worse. But it's called chain of thought. And you can actually go back and you say, oh, well, why did you say that's the only water park? Are you sure there are no others? And then it might say, well, this is how I came up with this, and this is why I can't tell you if there aren't any others. So you can interrogate these large language models a little bit to try to understand how it reasoned to get to whatever answer it gave you. Again, we're not 100% sure we can trust what it reports and how it reasoned or how it came to those, but at least there's some ability to interact and interrogate them on that. Now, for things like object recognition, these computer vision systems, I showed that we were like putting these little, each car or truck was a two-dimensional point, right? But in fact, these are images, and even, the basic images are what, maybe like, 1,000 by 1,000 pixels. So that's 1,000,000 numbers right there. So I couldn't draw the picture, but there'd be points in a 1,000,000 dimensional space. And then they go into these YOLO neural network or something, and then we have, representations that are recursively sort of improved as you go through the layers of these neural networks. Those representations are still very high dimensional, maybe 1,000 dimensional. And so we're really talking about very high dimensional spaces where things can look very good and, think about it, those are all the directions. In normal space, we just have 3 directions we can go in, right? But there you can go in 1,000,000 different directions, and it might be great in all but just one direction. As soon as you move in that direction, something weird happens. You miss that car altogether. You can't understand. To our eyes, they look like they should be equally easy or difficult to recognize. But there's just a subtle difference in there, and the systems are not doing what we're doing exactly in terms of how they're recognizing these objects, and it's hard to understand. Now, when will the average person be able to get in there and sort of say, well, why didn't you, how is it that you could miss this one? Or where did it go wrong? Like what point in this deep neural network process did that signal not come through? Yeah, that's a good question. I mean, it might be hard, and I was going to mention this before, one of the things we do a lot is we'll say like, oh, this AI system isn't working well. Well, how well are we doing it? So a good benchmark comparison is you give it to 2 students, and how many of misses or disagreements are there about whether that's really another car or just part of a shadow or something. So it's good to calibrate our expectations with that, but even if one student sees the vehicle, the other person misses it, well, why did they miss it? Yeah. I'm not sure they could explain exactly why. You would say there was the car, and they're, oh, I don't know, I'm not sure why I missed that. One of the biggest sources of error in medical diagnosis is different doctors see different things, right? It's just these are complicated, high-dimensional problems. Lots of things going on. Lots of context around that vehicle or not vehicle, the shadows, the foliage. And all that affects how we interpret and see those things or miss them mistakenly. So, yeah, I think it's, there's sort of, again, how do we understand how it is that our systems are doing what they're doing? We know some things. We know, we don't know more than we know about how we operate, and I think we're going to be in the same situation with AI for a while. The beautiful thing about AI, though, is it's kind of a pain to go into your head and figure out what's going inside without hurting you. With these systems, we can go in and get into the nuts and bolts of the internal mechanisms and try to understand them. So I think we have a better shot at understanding AI maybe than we have a understanding of how cognition and consciousness works in the brain. I don't know if that's reassuring or not.
Yeah, I don't know either. All right. I think we have plenty of time for questions. I know there's people with mics. So yeah. So if you wait for the mic to arrive.
Well, first of all, when you told me the number of images, that answered my first question, which is, a really neat thing about cars is that they move. And so I was hoping that perhaps you would be doing a differential comparison from image to image to be able to find them, but it sounds like you had a really long breaks in time.
Yeah.
My next one came to the scatter diagram, the clustering diagram you had on the cars and buses, because when you were discussing that, it brought me back to over 40 years ago, because I worked in machine vision at GE when embedded processors were first coming out. And I guess my question is this. So the explanation is, you've got an n space, you've got features and n dimensions, you're coming up with hyperplanes to separate them into clusters, you're measuring distances between them, and you're coming up with how many distinct objects you think you have. And that's how I kind of heard. Is that an accurate representation of what you were saying?
Yeah, I think in this case, we know we have two clusters because we've trained on them, buses and cars. And then there may or may not be some other groupings, but we're just calling everything else not bus,
out
not
of
car.
detection. Yeah, so my question is, since I understand the old world, having worked by hand, doing all the math, computing all those unusual distance metrics between presumably new objects, is that completely done the same way in the AI, or is the architecture so different that it's able to do something analogous to what we used to do with that math? Is it doing it in an entirely different way, or is it just doing it faster and quicker?
Yeah, I think the best way, and I'm not sure, let me see if this makes sense to you, but what's happening is as you go through these different layers in a deep neural network, you're basically progressively learning better and better vector representations of these objects. So it's sort of like doing in an automatic way through training, trying to find the best geometry, if you will, in which to represent these different categories of objects. And so that it's basically learning good features. It's taking the raw features, which are the raw images, and then crafting through the mechanisms of this training process really, really good features that are, and we can go in and look at those sometimes. We can say, oh, look at that. This feature is a feature that's detecting the wheel of a car. This is a feature that's detecting the hood of a car, right?
So it's like throwing out certain features, keeping some of them, and then weighting them differently, which in my old world would shift the space itself that you were measuring in.
And the old way, I think, let me see if this is right, we would sit down, we would put on our thinking cap, and we'd say, oh, well, let's hand design, handcraft, or engineer what we think are the features, the visual features that we should be paying attention to make these classifications. Now, we're not doing any of that handcrafting or engineering. It's all being just learned by millions or billions of images that we now have. So that basically the internet enabled that. If we didn't have the internet, we wouldn't have had all these images to train on. But because we have millions and billions of images, that changed the game completely. That was the driver of all this.
Well, hopefully you still have them do some of them by hand, just so you can feel the pain.
Just so we don't feel like we're totally unnecessary.
Thank you very much for the talk today, y'all. It was wonderful. One of the earlier points that you brought up was like the proxy problem, where you're optimizing some sort of proxy metric that might not actually necessarily represent what you're trying to get at in reality. And then that kind of made me think of the kind of like the difference between like a snowy driveway and a clear day is like, is there a way that you have kind of this like diversity of metrics that you're looking at to try and like whether that's like using different types of sensing, different resolutions as a way to like resolve the proxy problem that you're looking at, maybe different features in those spaces.
Yeah. So, I mean, one of the problems, maybe I'll just rephrase and restate the problem a little bit. People publish data sets. They say, here's a data set on, and the challenge is object recognition. Or here's a data set, and the challenge is predict the values of the stocks the next day, right? And then machine learning AI people go to work. They take that data, they train up these models. They say, oh, I think I have a better way to model this. I can make these changes to the way the deep neural network is architectured. That should give me some boost. And so they really just keep hammering on these training sets. And so what we can get is kind of like overfitting to the idiosyncrasies of the data set, and then we're not really robust or working well once we move outside of that. So that's sort of like this proxy thing. The data set itself is sort of a proxy for the real world. Now, everything I talked about is trying to guard against getting too hung up on high accuracy on the proxy, and instead maybe giving up a little bit on that in return for some more robustness and resilience to the real problem, which is out there in the real world. So all the things we mentioned, like enhancing your data set, changing the way, you have a choice about how you measure accuracy too, right? I could sort of say, like, if I want the neural network to output a number, I could say, well, look at the difference between what it put out and the number it was supposed to get, and look at its squared difference. That's one measure of error, but we could also have other measures of error that are either less sensitive to outliers or more sensitive to outliers, so we can look at different ways to measure error, and that will affect how the system learns and trains up. So there are a lot of different elements of the process that can be changed or added to make the systems handle some of these problems of overfitting to a problem that's not really the real problem.
This is quite different than what you've been talking about, but I'm just curious to get your opinion on it. ChatGPT is supposedly coming out with a health app, and everybody in the world, including myself, is on the wait list for it. And so you're going to be able to take and contain yourself a walled garden of what your data is and bring it in and privately and interact. But then the question is, if it suggests different things, how can you check that against some other, your general information about that?
Yeah, so that's a great question, and I've talked with my mom and dad a lot about this because my dad's pretty elderly, he's like 90, and he has a lot of issues. The systems are starting to break down, and he had something come up. So I asked ChatGPT. I asked Gemini, I think, first, and Gemini was pretty cautious, didn't want to say too much, said talk to a doctor, and they really had some guardrails on it. ChatGPT, less guardrails, which is good and bad, but it gave me all sorts of information. But the beautiful thing is, it also gave me links to all the places, all these, NIH, published articles. Now, again, you have to decide whether you want to take the time, but it did give me the paper trail that I could go back and see, oh, it said it got this out of this journal article. Again, it depends on your level of understanding of these things, but I went and looked at some of those articles to make sure that I was trusting what it was saying. And so I was actually pretty impressed because it gave me the hardcore evidence that it was drawing on for some of the recommendations and so forth that it was producing. So I think, just like anything else, if you go to a doctor, you get a second opinion, you might look up some stuff on yourself. I don't think it's a one-stop thing. Just take the advice from the AI system and trust it. I mean, I think you want to trust and verify. Mm-hmm. Yeah. We didn't. Yeah. Yeah, although I really like the fact that this is much more interactive. Like I can kind of sort of start dialing in it a little bit. Like I'm like, well, no, really, I don't know, headaches weren't such a big part of it, but nausea was more of a thing. Like you can start, I don't know, it just feels like much more efficient way to get to the information I need. And then again, once I get there and I think I've homed in on what I'm interested in or what I think is diagnosing my situation, I can check the evidence. And that's what, so I'm pretty happy with it, to be honest. But I think, it's sort of the buyer beware. You have to check. Wow, yeah. Well, that's getting complicated. I think any help is going to be helpful, right? Because even, I don't know, I look at what my dad's on and I'm like, what is this for? He's like, yeah, I can't remember, right? Because there's so many. And I don't know, well, to be full disclosure, he's in hospice and he's been there for a while. He got off all the meds and he started actually being better. So I don't know. I'm not sure who to trust, right? I don't want to sound like a crazy person, but I'm just saying medicine is very complicated. Our human bodies are very complicated. It's another area where there's still a lot to learn.
Oh, maybe back.
So these are great examples of using AI. When should you not use AI?
Do you want to try take this one first?
So I'm a huge AI skeptic. I hate AI, and the reason I hate AI is because I can't trust it at all. So I'm a historian, so I've tried to use AI to help me with my research, and so I have a few baseline questions that I ask AI, and they're questions that only I would probably know the answer to because of the esoteric nature of them, and it gets it wrong every time in a different way. And every time I tell it the correct answer and where it can get the correct answer, and it never seems to learn. But even more nefarious than that, I will ask a question like, did any US congressman give a speech on the House or Senate floor between, let's say, August of 1949 and December of 1950? And it will say, yes, 7 did. And I'll say, great, which 7? And then it'll say, I cannot give you that information. And I say, well, why did you tell me that there were 7 and who were they? And it just starts to break down there. So I often cannot get the paper trail that I'm looking for.
And then I wouldn't trust it, yeah.
And then you can't trust it. And so then it makes you wonder, even when it is telling you information that you think is more or less accurate. Mm-hmm. So I feel like for the purposes of a historian, it's so seductive, but it's also so dangerous because it seems like it can help you do all this stuff. But if it's not pointing to sources that are actually real that you can verify, you can't use it.
Yeah. I think another place where you don't want to use it is, it's a great tool for writing. If you have to write a report that you don't want to write and nobody's going to read it anyway, use AI. But if you want to do something creative, probably, it can make you sound like a great writer, but it won't be your voice. So actually my son he took an English class and he had to write an essay. He's like, oh yeah, I'm just going to have ChatGPT write it. And what was the essay? You were supposed to write one paragraph about a place, a scene that you were in, one paragraph in a positive light, one paragraph in a negative light. So he happened to be a bouncer at a bar at the time. So he wrote about the bar and he gave it to ChatGPT with a little bit of prompting about what the situation was. And it came back with something. He's like, yeah, isn't that great? I go, no, it's totally boring. I said, what would you say? And he wrote, and I'm not going to go into the details because some of it's not safe for work or whatever. Like he told the real story of what was going on in the bar that night. And it was much more entertaining, much more real. And so if you want to do your own creativity, probably have to at least keep AI out of some of it. That's one thing. The other thing is, in my line of work, we're not so much asking questions about politics or history, but we're trying to get help with understanding AI systems, and a lot of that understanding comes through mathematical reasoning. So we use AI systems to help us mathematically reason about problems, like basically prove mathematical theorems that we think are true but haven't been proved yet. And basically what I've seen happen is the earlier versions of like ChatGPT would often come up with proofs that if you then go through and check the reasoning and the logic, it's flawed. The latest version, so one of my former students who's a professor at Washington, he convinced me to pay for Pro. This is the $200 a month version of GPT. And now it still can't prove new theorems, but at least it can tell me that it doesn't know how to do it. So, so now it's not giving me false hope. It's just saying, yeah, I don't know how to do it either. So, yeah.
All right. Well, unfortunately, that is all the time we have. Please join me in thanking Rob for his time.
Thanks, David, too. Yeah. It's great.
I know, I think when we use Gemini and Google Earth, I think it actually